differentiable. Now, for this purpose, for any y in V, we will prove that phi is differentiable at y. So we want to say that phi is differentiable at y. How to prove this? So we can only use the definition of differentiability. Therefore, for k in Rn not zero and small, k small means the norm of k small, meaning that the norm of k is very, very small, much smaller than 1. Okay, so we let x to be phi y. This is the same as fx equal to y, because f and phi are inverse to each other. Okay, so we let x to be the phi y, and we take an h to be phi y plus k minus phi y. Then how about y plus k? Then y plus k is f phi y plus k. Okay, because f and phi are inverse map to each other, so this is f x plus h. Phi y plus k, from this equality, phi y plus k is phi y plus h, but phi y is x. Therefore, we can write this as fx plus h. And the norm of h can also be estimated to be phi y plus k minus phi y. This is less than 1 over lambda, and the norm of k. So this means that when k goes to 0 implies h goes to 0. Okay, the inequality means that when k goes to 0, we have h goes to 0. Now, k is not 0, because we take k not 0, and phi is injective. Therefore, we conclude that h is not 0. Okay, h is not 0, because h is phi y plus k minus phi y. Since k is not 0, y plus k is not y, so phi y plus k is not equal to phi y, so h is not 0, because h is precisely phi y plus k minus phi y. Okay, this is our h. So having this parallelization, we can estimate this phi y plus k minus phi y minus the derivative of f at x. This is a matrix, invertible matrix. So we take the inverse and apply this to k, then divided by the norm of k. If this goes to 0, as k goes to 0, then by the definition of differentiability, this means that phi is differentiable at the point y, and the derivative is the inverse, is this matrix here, and our result is proved. Okay, so we need to prove that this fluxion goes to 0 as k goes to 0. So we estimate this fluxion. Now we estimate this. Estimated the fluxion. This is phi y plus k minus phi y is h minus the inverse matrix of f prime x k, then divided by k. But we can write the numerator to be the inverse matrix of the derivative, and then the derivative apply to h minus k. Okay, k is what's k? We observe this equality. K is fx plus h minus y, but y is fx, so k can be written as fx plus h minus fx. Okay, so the numerator can be written in this way, and the denominator will remain keep the denominator k, and then we use the definition of matrix norm. The numerator is a matrix, the inverse matrix multiplied by the vector and take the norm. This norm will not greater than the norm of the matrix. The norm of the matrix multiply the norm of the vector. The vector is fx minus fx plus h minus fx. Okay, but you can also write this in another way. You can also write this term by, because a vector, the norm of a vector is the same as the negative vector. Okay, so this can also be written as fa plus x plus h minus fx, then minus the f prime x h, then take the norm. And the numerator k, we can replace the numerator by the norm of h. Because h is not zero, we emphasize h is not zero here. Therefore, the norm of h is not zero. So we can divide it the norm of h, and then we we write it in this way, because these two can be cancelled, and then this is the original denominator. Therefore, we can using this trick. Now we observe what this the behavior of the right hand side. The right hand side, this term is bounded. This term, the norm of h divided by the norm of k is bounded. It will not greater than 1 over lambda. Following this formula, following this inequality, the norm of h divided by the norm of k will not greater than 1 over lambda. Therefore, this is bounded. Okay, bounded. And this term is a fixed number. The norm of the inverse matrix is a fixed number. Does not depend on h or k. Therefore, this is a constant. For the fixed x, this is a constant, so we don't care about it. Okay. Now this part by the differentiability of f at the point x, this part will go to 0 if h goes to 0. Okay, but when k goes to 0, we do have h goes to 0. So when k goes to 0, h will goes to 0. Therefore, this part we are the part we care about goes to 0. This part will goes to 0. In conclusion, the right hand side goes to 0 as k goes to 0. Okay. So this means that the left hand side is this. The left hand side is this part. This goes to 0 as k goes to 0. So this precisely means that phi is differentiable at y, and the derivative of phi at the point y is precisely the inverse matrix of f prime x. Okay, so this proves the conclusion of the inverse function theorem. Okay, so we have proved the inverse function theorem. The inverse function theorem says that for a map F from an open subset in Rn to Rn, if the linearization of the map at the point A in omega is invertible, then F itself is locally invertible. Okay, so the inverse function theorem applies to maps from Euclidean space of the same dimension. The domain of definition is n dimension, and the domain of the image is also n dimension. The dimensions are the same. But in many applications, we encounter the maps from between space of different dimensions. Okay, so for example, sometimes we need to study a map also from n-dimensional omega, but to Rm, another Euclidean space. And for such a map, if A is a point in omega, the derivative is a linear map from Rn to Rm. If n and m are not equal, such a map, this linearization, could not be invertible. In linear algebra, we know that for linear map between finite dimensional space, if the linear map between finite dimensional space is invertible, then the dimensions of both spaces should be equal. Okay, but now if n is not equal to m, then this map could not be invertible, but it could be injective or surjective. So in the spirit of the inverse function theorem, that is the linearization, the property of the linearization, that is the derivative, would be inherited by the original map locally. So if the linearization is surjective, it is 1, 2. What can we say about f? Can f be surjective? Of course, locally. Can this be true? So it turns out that this is true, and this is a very useful result, and it demonstrates a typical method to apply, typical style to apply the inverse function theorem in other problems. Therefore, we will discuss this result here. This is a theorem. Let omega be open subset in Rn, and A is a point in omega, and our map F from omega to Rm is say 1, continuously differentiable. Okay, now suppose Fa, the image of A is B, then if the rank of the Jacobian matrix, the rank of the derivative matrix is the dimension of the target space M. In this case, from linear algebra, we know that this condition means that this map is surjective. Okay, so this is the surjectivity assumption for the linearization. Okay, so in this case, we say that we conclude that B is an integral point of the image of F. So this is the conclusion of this theorem.